Section 8.2, Lesson 1, Integration by Parts. Our objectives for today are: you will understand the development of the integration by parts formula. It comes from the product rule, and we'll see that. You will memorize the integration by parts formula. You'll be able to choose U and dV appropriately by using guidelines. So this is basically going to help you with applying the integration by parts formula. Vocabulary. We'll begin with an activity in which we review integration by substitution, and then we'll move on to a new technique for integration called integration by parts. And of course, you learned about the fundamental theorem of calculus, which you can use to evaluate definite integrals which have limits of integration, lower and upper limits of integration. If you have an integral without limits of integration, you have an indefinite integral. The function inside is called the integrand, and when you're working with an indefinite integral, you're looking for an antiderivative of the integrand, and of course you need to add plus c, which is called the constant of integration. So we begin with this problem, and this is a review of integration by substitution, and here is how you would do this problem. So you look at this problem, it's an indefinite integral, there are no limits of integration, and this is of course the integrand. So you're looking for an antiderivative, a function whose derivative is this integrand, and you will have a constant of integration plus c. Now there are some problems that are really easy to do. For example, we know that the derivative with respect to x of sine x is cosine x. So if you have the indefinite integral of cosine x dx, you know what the antiderivative is. An antiderivative of cosine would be sine, because the derivative of sine is cosine, and you write plus c. So that was a really easy problem. But when you have something like the one that we are working on, you may not know right away what an antiderivative of the integrand is. So you have to try to do it in such a way so that you can figure out what the antiderivative is. So integration by substitution allows you to rewrite the problem so that it is easier for you to find an antiderivative. Integration by parts is a similar idea. It allows you to rewrite a problem so that you have one in which you can figure out an antiderivative. But when would you do integration by substitution? If you can find a substitution that works, such as in this problem. When would you do integration by parts? You would try integration by substitution because you might find that to be an easier way of doing it. But if integration by substitution does not work, you've got to try something else. And one of those other possibilities is integration by parts, and that's what we'll look at for our lesson today. But let's quickly review integration by substitution. So in this case, you're looking at the integrand, and one of the questions that students ask is, how do you know which particular technique you should use? And it comes with experience, but there are also certain things that you can look for in the integrand that will give you a hint about what technique might be appropriate for the particular problem that you're looking at. So when you look at this integrand, you see that in the denominator you have a square root. And we do know how to work with problems of this type. For example, if you have this, what is the integrand here? The integrand is 1 over the square root of u. And the square root of u can, of course, be rewritten as u to the 1/2 in the denominator, which can then be rewritten as u to the negative 1/2 using properties of exponents. And u to the negative 1/2 is a power function, and it is easy for us to find antiderivatives of power functions by using the power rule for integration. So with that line of reasoning, and because I see the square root in the denominator, I'm going to try to do a u substitution that would give me what I had written and then erased, which was, of course, this. I want to see if I can get something like this because I know how to work with this. So my u substitution will look at the radicand, which is 1 minus x squared, and I would like to let u be equal to the radicand so that I can have square root of u in the denominator because I know how to work with that, and you see my work for that. We will go over that now. So that's kind of like letting you know that you should try this u substitution. So if you let u be equal to 1 minus x squared, the next step is to find what we call the differential of u. The differential of u is the derivative of 1 minus x squared multiplied by the differential of x. dx is the differential of x, and this is what we mean by differentials. So the derivative of 1 minus x squared is negative 2x. So now when you do integration by substitution, this is your substitution, and then you're going to have something called your change of variables step, where you change from integration with respect to x to integration with respect to your new variable u. And when you do your change of variables step, everything must be in terms of the new variable u. And this will help us to make that change of variables be successful. So you see here that we have x dx. So I let u be equal to 1 minus x squared, which is the radicand here. So I have now the differential of u is the derivative of 1 minus x squared, which is negative 2x times the differential of x. And then I see x dx as a part of my original problem. So we're going to go ahead and solve for x dx here. And when we do that, we get du over negative 2. And with this substitution, we're able to do the change of variables step. So I will replace the radicand with u, giving me square root of u in the denominator. And I will replace the x dx with du over negative 2. But of course, you have a factor of 1 in the numerator of the integrand. That's what I have here. And then you can factor out the constant factor of negative 1/2. So that's what I've done here. So now I'm left with the square root of 1 over square root of u du. And of course, the square root of u is u to the 1/2. And this is a power function that I have in the integrand. And using properties of exponents, I can write this as u to the negative 1/2. And this is a power function. You may remember something called the power rule for differentiation. The power rule for differentiation states that if you have a power function, to find the derivative, you bring the exponent to the front, and then you subtract 1 from the exponent. The power rule for integration does the inverse of that. So you're going to add 1 to the exponent, and then divide by the new exponent. So when you add 1 to negative 1/2, negative 1/2 plus 1 will give you positive 1/2, and then you divide by 1/2, which is the same as multiplying by 2. So I have used what we call the power rule for integration to find an antiderivative of u to the negative 1/2. So my substitution was successful because it allowed me to find an antiderivative. So, but I want to go back to my original variable, which is x. Right now I have my antiderivative in terms of u. But I can do that easily by going back to my substitution here. So u to the 1/2, you can write u to the 1/2 as the square root of u and replace u with 1 minus x squared to get the square root of 1 minus x squared. You have this 2, which is right here. And then you have the plus c, which is called the constant of integration. Multiply negative 1/2 times 2, you get negative 1, and this is the antiderivative. We have found the indefinite integral. So we spent some time reviewing integration by substitution, and now we're ready to think about a new technique for integration called integration by parts. We will begin by thinking about how it is developed, where does it come from, and then we'll look at the integration by parts formula and guidelines for doing it. And a couple of examples will follow after that. So we just reviewed integration by substitution, and now we're ready to move on to integration by parts. So we will begin by looking at where this integration by parts formula comes from. We'll look at the development of the integration by parts formula, and then once we have it, you should memorize it, and then we'll look at guidelines for using the integration by parts, and we'll look at a couple of examples to conclude the lesson. So where does this integration by parts formula come from? Consider this. We know the derivative of sine is cosine, so the derivative with respect to x of sine x is cosine x. So if you have the integral, the indefinite integral of cosine x dx, we know we're looking for an antiderivative, and of course, the antiderivative or an antiderivative of cosine would be sine, so we write sine x plus the constant of integration. So we know that. So now we're going to take a look at something from Calculus AB called the product rule. So here we have the product rule from Calculus AB. If you have a product of two differentiable functions, to find the derivative of the product, here's one version of it. Find the derivative of the first function, multiply by the second function, and add to that the first function times the derivative of the second function. So that's g prime of x, the derivative of the second function. So the derivative of the first function times the second plus the first function times the derivative of the second. So that's the product rule. And I want you to see the product rule like we saw this particular differentiation rule. So you have the derivative of sine x is cosine x. The derivative of a product is given right here. So what did we do after we looked at the differentiation rule for sine x? We looked at the corresponding integration rule. So we took the indefinite integral of cosine, and of course an antiderivative would be sine x plus c. So now we're going to look at the indefinite integral of the right side of what we wrote here for the product rule. And when we do that, this is what we should get. When we take the indefinite integral of f prime of x times g of x plus f of x times g prime of x dx, we know that an antiderivative of that would be f of x times g of x. So I write this equation. And we're going to work with this equation by doing a substitution, which will lead us to the formula for integration by parts. So where does the integration by parts formula come from? It comes from the product rule. Our next step in the development of the integration by parts formula is to make this substitution. We're going to let u be equal to f of x, and we're going to let v be equal to g of x. So now we will find the differential of u. The differential of u du, by definition, is the derivative of f of x, which is f prime of x, multiplied by the differential of x, which is dx. And we'll do the same thing for v. We will find the differential of v, dv. By definition, it is the derivative of g of x multiplied by the differential of x. So now with this, I'm going to change variables. So wherever I see f of x, I can replace with u, and wherever I see g of x, I can replace with v. So my equation that I have here, which I'm starring green, can now be written as u times v is equal to, and on the right side I have this indefinite integral, and the integrand is a sum. So if you have the indefinite integral of a sum, you can write that as a sum of two indefinite integrals. So we're going to go ahead and write this as a sum of two indefinite integrals using a property of indefinite integrals. So we're going to write it like this. So now we'd like to rewrite the right side of the equation that we have. So the left side is uv, and the right side, take a look at what we have here. We have f prime of x dx. And f prime of x dx, if you look over here, is du. And g of x is v. So we can write this as the indefinite integral of v du. And then plus, here we have g prime of x dx, and g prime of x dx is dv, and f of x is u. So this will be u dv. So what I'm going to do now is I'm going to erase what we started with, because I need some room to finish the problem and I want everything to be on the same screen. So I'll just erase the work that we did at the beginning. So the integration by parts formula comes from the product rule, which I wrote here, and I'm erasing it now. And our work developing the integration by parts formula started here. So we started here and we're going to end above that. So now we're going to take what we have here and bring it over here. So what are we going to do next? We're going to manipulate this equation so that we are subtracting the indefinite integral of v du from both sides of the equation. So we're going to have uv minus the indefinite integral of v du is equal to the indefinite integral of u dv. And this is actually the integration by parts formula. It's just that this is written on the left side and this is written on the right side. So we're going to write the indefinite integral of u dv is equal to uv minus the indefinite integral of v du. And this is called the integration by parts theorem. Integration by parts. And as you saw just now, we derive it from the product rule that we learned in Calculus AB. Now you might say, what's so great about this? Because I began with an integral and I have an integral here. And yes, that is in fact a part of the process for integration by parts. And the whole idea is this. You begin with a particular integration problem that you don't know how to do, and if you apply integration by parts, you're going to rewrite your problem as you see on the right side of the integration by parts formula, and you will still have an integral. But you're hoping that the integral that you have on the right side is something that you do know how to solve, something that you do know how to find an antiderivative for. So the idea in general is similar to what we did with integration by substitution. You're trying to simplify the problem that you're working on to something that you know how to solve. But with integration by parts, because it comes from the product rule, usually you will apply integration by parts to integration problems where you have some kind of a product in the integrand. Now we're going to conclude our lesson by looking at two examples for applying the integration by parts formula. So theorem 8.1, integration by parts, we just developed it, so we know where it comes from. So these are guidelines for applying the integration by parts formula. So these are some general guidelines that we can try when we're looking at a particular problem. So let's look at an example and then we'll see how to apply these guidelines. So here we have example 1 from section 8.2 of the textbook. And we're going to take a look at how to apply the integration by parts formula. So you might want to try to do integration by substitution, but you're not going to succeed. There is not really something that you can choose for you so that you'd be able to do a change of variables which will allow you to solve the integral. So integration by substitution is not the way to go here. So now you think, what else might we be able to do? Integration by parts seems like a logical alternative. Why? Because you can see a product in the integrand. So let's try integration by parts. So how do you decide what u and dv should be? When you do integration by parts, you've got to begin by letting u, so you've got to let u be a part of the integrand, and the rest of the integrand will be dv. And the whole purpose for doing this is so you can start the process, and you're hoping that you're going to choose u and dv in such a way so that the integral on the right side of the integration by parts formula will be something that you can solve easily. Now, sometimes you'll choose u and dv in such a way so that that doesn't happen, or it doesn't work out. So if that's the case, what do? You go back and try choosing u and dv differently. So you have to try different combinations of u and dv until you get something that will allow you to solve the integral on the right side of the integration by parts formula. There are some guidelines that should help you to choose u and dv correctly on the first try. But if for some reason you don't choose u and dv correctly on the first try, just try again with a different choice for u and different choice for dv. So what are the guidelines? Let's take a look over here. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. U will be the remaining factors of the integrand, and guideline 2 is just a different way of stating guideline 1. Try letting u be the part of the integrand whose derivative is a function simpler than u. dv will be the remaining factors of the integrand. So let's go ahead and try something here. So we're going to try letting u be equal to x. That's a part of the integrand. And the derivative of x is 1, which is simpler than x. And we're going to let dv be the remaining part of the integrand. dv will be e to the x dx. So now we will find du. If u is equal to x, then the differential of u, du, will be the derivative of x, which is 1, multiplied by the differential of x. If dv is equal to e to the x dx, then we can find v by integrating both sides of that equation. So you have 1 dv, so you take the integral of that, and then you take the indefinite integral of the right side of the equation. So an antiderivative of 1 is v, so you're going to have just v here. And on the right side, an antiderivative of e to the x is just e to the x. So you'll have e to the x. Normally you would write plus c as your constant of integration, but you don't have to do it when you're doing integration by parts, because at the very end of your work you will write the constant of integration. So now we know u, we know dv, we know du, and we know v. So let's go ahead and rewrite our problem that we have here using the integration by parts formula. And we're hoping that when we do that, the integral that we have on the right side of the formula will be something that we know how to solve. And if it isn't, you may need to go back and adjust your u and dv. But it should work for this particular problem. So let's go ahead and see that it does. So you're going to write x times e to the x dx, which is our original problem. And using our work here, we're going to apply the integration by parts formula. So now we're going to write u times v minus the indefinite integral of v du. So u is x, v is e to the x. And you see that u is x and v is e to the x. So we write u times v, x times e to the x, minus the indefinite integral of v du. So minus the indefinite integral of v, and v is e to the x, v du. Du is 1 times dx. So that's going to be that. And of course, this is great because you know what this integral is. It's e to the x. So this is an example of a successful application of integration by parts. Because now, what was originally something that we could not do has now been rewritten using integration by parts so that we can do it. And if we had chosen u and dv differently, you can try it and see what happens. It would not work. So you would just keep trying different choices for u and dv until you find that this one does work. But of course, if you understand the guidelines, you're more likely to get the correct choice for u and dv on your first try. So now you have this. So this indefinite integral is e to the x. So now this is our final answer. And for our final answer, we write the constant of integration. So here we look at example 2. And this is what we have for the integrand, x squared times natural log of x. You look at this and you think, I'm having some math indigestion. I need to get my Pepto-Bismol. So now what are you going to do? You're going to take a breath and you're going to think about how you might be able to do this. Integration by substitution is not going to work here. So you're going to think, maybe I can do integration by parts. And why is it that you can do integration by parts? It'll work out, but one thing that gives you a clue that integration by parts might be appropriate here is you see a product here. And because you see a product, you're going to think, maybe I can do integration by parts. So what are you going to do? You have to choose u and dv. So you have to think, let u be equal to which part of the integrand. Let dv be equal to which part of the integrand. So look at the guidelines here. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Number 2 is saying the same thing but in a different way. Try letting u be the part of the integrand whose derivative is a function simpler than u. Now here's the deal. You don't want to do this. You don't want to let dv be equal to the natural log of x dx. Why not? Because to find v, you would have to integrate. So v would be the indefinite integral of natural log of x dx. And at this point in time, we don't know what this indefinite integral is. So this is not a good choice for dv. Because remember, look at guideline 1. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. We don't have a basic integration rule for natural log of x. In fact, we can use integration by parts to find an integration rule for natural log of x, and that will be in lesson 2. But we don't have a basic integration rule for natural log of x. So this is a poor choice for dv. So what are we going to do? Well, if natural log of x dx cannot be dv, then naturally we're going to let natural log of x be u. So if that's u, then what's v? So we've got natural log of x is u, so what's left? X squared dx, so that's going to be dv. So we have x squared dx, that's going to be dv. So now we're going to find du and v. So then du, I know the differentiation rule for natural log is just 1 over x. So I have 1 over x dx for du. And to find v, you integrate both sides here. So when you integrate the left side, you get v. And when you integrate the right side, you just use the power rule for integration. So you're going to have x cubed over 3. Add 1 to the exponent and divide by the new exponent. And again, I will not write the plus c. That's going to be done at the very end of the work. So this is what we have, and let's see how this works out for us. So now we're going to use what we just did and the integration by parts formula to rewrite our problem, hoping that the right side of the integration by parts formula will give us something that is easier to do than what we have right now. We don't know how to do this, so we're rewriting it so that we will have something that we know how to integrate. So now we write our original problem is what we have right here. So the integration by parts formula is, and you need to memorize this, and here's some way that you might be able to memorize it. The indefinite integral of u dv is uv minus the indefinite integral of v du. I had a student a few years ago and he remembered it like this. Uv vadu. It worked for him, maybe it will work for you. But now let's go ahead and do it. So we rewrite it using uv minus the indefinite integral of v du. So uv, so you do natural log of x times x cubed over 3. So when you do that, you get x cubed times natural log of x over 3. So that's uv minus the indefinite integral of v du. So here's v, and here's du. So v du will be x cubed over 3, that's v, and du is 1 over x dx. So when you multiply here, you will be able to cancel the common factor of x that you have in the denominator here with one factor of x in the numerator. So this will become x squared. And then you are able to do this. You can factor out the 1/3, and you will have the indefinite integral of x squared dx. And we're happy now because that is something that we know how to integrate. This can be easily integrated by using the power rule for integration. So we have x cubed natural log of x over 3 minus 1/3. And the antiderivative here would be add 1 to the exponent and divide by the new exponent plus the constant of integration. And of course, you can multiply the 1/3 here with the 1/3 here to get 1/9. So we can do that. That's one way you can simplify. So you have x cubed over 9. Another possibility is you could have factored out 1/3 from both of these terms that you have here as well. So either way is fine, but this is our antiderivative, and you have the constant of integration there. So we began our lesson for today by reviewing integration by substitution, and then we looked at the development of the integration by parts formula. So now you should memorize the integration by parts formula We looked at some guidelines for applying the integration by parts formula, and we also looked at a couple of examples for integration by parts.